Well, my first love is doing mathematics, and the mathematics that I really love doing is trying to understand the world of symmetry. And so if I was cast out and I had to spend the rest of my life in just one building somewhere around the world, then it would be the Alhambra that I would choose to be banished to, because this for me is a real palace celebrating the subject of symmetry. What I would like to do is to give you a little bit of a mathematician's perspective on how I see this world of symmetry, and in particular what I see when I go around the Alhambra. I'd never thought of mathematics being a language before, but actually it's an incredibly powerful language. It's a language which helps you to understand where we've come from, what's going to happen next. Symmetry is, in a sense, a language which nature uses to communicate. If you take a bee in the garden, a bee has very bad vision. It can't judge distances, it sees the world in black and white, but what it can pick out is shapes with symmetry, because it knows that that's likely to be a flower with sustenance. The flower itself also needs to have the bee coming to it to propagate its genetic heritage. So in some ways the symmetry is being used like a billboard, communicating between the bee and the flower. In fact, it's said that researchers found that the more symmetrical a flower, the sweeter the nectar inside the flower. Humans too, we also use symmetry as a way to communicate information. Here are two faces which I've made artificially symmetrical down below. Now, if I ask you which of these do you find more beautiful, most people are drawn to the artificially symmetrical ones. Why is that? Because actually it's communicating information. It's very difficult to make symmetry. So if you can make your face perfectly symmetrical, you're actually giving a signal. You're telling somebody that your DNA, your genetics is very good, or your upbringing is very good, and you're going to make a good mate. Plato got to something which is really at the heart of modern science, which is that you find symmetry, the mathematics of symmetry, underpinning so many different bits of the scientific world. So, for example, molecules, what crystals are possible. If you understand symmetry, you understand why crystals, which may be made out of different things, will behave in a similar way. In biology, actually, you don't want to get a symmetrical object because they're rather nasty. A virus is actually symmetrical, and it uses the symmetry as a powerful way to propagate itself very quickly, because it's a very efficient program to make more copies of itself. So, for example, the H1N1 virus was in fact a symmetrical object. So understanding its symmetry gives one some understanding of what it might do. But it's not just scientists who are interested in symmetry. The artists too have a fascination with this world of symmetry, but they have a slightly more ambiguous attitude towards it. Here's Thomas Mann writing in The Magic Mountain about symmetry. He has a character who describes a snowflake and says, "I shuddered at its perfect precision, found it deathly, the very marrow of death." And I think for many artists, symmetry is rather constricting because it sort of forces you to do certain things. So I think there's a little bit of tension with this world of symmetry. Of all the buildings in the world, I think the one which really celebrates symmetry is the Alhambra. But of course it's on the walls really, I think, where the beautiful symmetrical games are being played. And for me as a mathematician, this palace really poses all the interesting questions about symmetry. What exactly is symmetry? If I showed my son this wall here and asked him, does it have any symmetry? And he said, no, it doesn't look symmetrical at all. But what he was looking for was left-right reflectional symmetry. This doesn't have any left-right reflectional symmetry, but it does have symmetry. But what does it mean to have symmetry? Also, how can I articulate that two of these walls have the same symmetries? How can I say if the Moorish artist discovered all the symmetries that are possible on the walls in the Alhambra? Now, actually, to be able to articulate these ideas, the Moors didn't have the sophisticated language to be able to talk about these questions. In fact, it took a mathematician called Évariste Galois, who was a French revolutionary who discovered a language to be able to articulate the games that are going on in the Alhambra. Now, Évariste Galois had an incredibly dramatic life. He was in fact shot in a duel at the age of 20 over love and politics, it said. But already by the age of 20, this young mathematician had already cracked one of the great mathematical problems at the time, which gave him this insight into how to understand symmetry. That language he left for us, a language that we call group theory, has enabled us to actually navigate this world of symmetry. This 18-year-old boy had developed a new way of looking at symmetry, which enables us to answer those questions about the Alhambra. And what Galois realized is that really symmetry is like the magic trick moves. What can I do to these tiles? I can move them until suddenly they all line up again, and I can put them down exactly where they were before. So I like to describe symmetry as the magic trick moves. If you close your eyes and I pick up these tiles and I move them around, put them back down again in a different way, you open your eyes, they don't look like they've moved. So that is what symmetry is for Galois. Actually, it's interesting because for mathematicians, symmetry is actually something with a lot of motion in it. It's got life, it's got movement. Unlike Thomas Mann, who thought it was very deathly. For a mathematician, it's the moves that you can make to the wall which are the key to symmetry. But what Galois realized, it's not just the individual moves, but how they interact with each other, which is key. So I'm going to push you a little bit mathematically now, so brace yourselves. But I want to explain this language that Galois developed to explore the symmetries of these two objects. So two simple objects. I've got a six-pointed star with a little twist on it and a triangle. So the magic trick moves, the symmetries, are the things that I can do to these objects which leaves them exactly where they were. So first of all, I could rotate it by a sixth of a turn. It looks like it did before. Okay, I can rotate it by a third of a turn, and still looks like it did before I moved it. Or I can rotate 180 degrees, half a turn. So that's three symmetries, or I can move all the way around to 2/3 of a turn. A fifth symmetry takes me 5/6 of a turn round. So there are 5 different symmetries that I can do to this starfish. Now actually there's a sixth symmetry that Galois identified here. The sixth symmetry is just leaving something where it is. So that, it's strange, it means that everything has one symmetry, which is just picking it up, putting it down again. Now, it seems a bit silly, but actually this is as powerful as the concept of the number 0. And we heard earlier about the Arabs. Actually, it was, the Indians were the first to develop the idea of 0. Beforehand, the Europeans said, well, why do we need a number for 0? If you're not counting anything, you don't need a number. But the Indians realized the power of 0 to actually make advances in mathematics. So here again, this is like the 0th symmetry, if you like to think about it. So there are 6 symmetries that this starfish has. Let's take the triangle. I can rotate that by a third of a turn clockwise, or a third of a turn anti-clockwise. I've got now I can reflect this, as you said. I can reflect in the line through x, or I can reflect it in the line through y, or I can reflect it in the line through z. So 5 symmetries again, plus the extra symmetry where I just pick it up, put it back down again. So both of these objects have 6 symmetries. So should we say they have the same symmetries because they have the same amount of symmetry? Well, no, you feel that there's some difference between these objects, but how can we articulate why the symmetries of these things really are different? For Galois, what he realized is it's the interactions of these symmetries which distinguish them. If I do one magic trick move followed by another one, the combination is a third symmetry. So you can actually develop a kind of algebra. If I do one thing followed by another, what's the answer? It's a third symmetry. So here I'm going to do a little bit of changing. This is the power of the language of mathematics. Galois changed geometry into a kind of algebra which tells me how the symmetries interact. So what I'm going to do, I've given names to each of the symmetrical moves. So A is just leaving the thing where it is. Capital B is the turn where the little yellow dot moves round to the lowercase b. So C is a third of a turn, D is half a turn, E round to here, and F there. Now what happens if I do a sixth of a turn followed by a third of a turn? So I'm going to do rotation B followed by rotation C, which is a third of a turn. And the combined effect of those is as if I'd just done half a turn in one go. So this table shows me how the symmetries interact with each other. And this was the inspirational move of Galois, is that this is key to understanding the symmetries of this object. If I do this in a different order, it doesn't matter really. Do the third of the turn followed by a sixth of a turn, it still ends up in the same place. So there's some symmetry in the way the symmetries interact. But that's not true for the triangle. Let's do two symmetries of the triangle. I'm going to rotate by a third of a turn anti-clockwise, then reflect in x. The combined effect is if I just reflected in z. But now do these in a different order. Do the reflection first, and then rotate by a third of a turn. It ends up in a different place. It's as if I'd reflected in the line through y. So the way these symmetries interact enables me to distinguish the symmetries of the triangle from the symmetries of that six-pointed starfish. And in fact, Galois developed a sort of set of rules for how the symmetries interact. It's a little bit like the rules for a Sudoku. I don't know whether any of you do Sudokus here, but remember, you're not allowed the same number in any column or any row. Well, that's the same for symmetries as well. You're not allowed any symmetry in the same row here in the main body of the table or in the same column. And Galois developed some rules for the way symmetries must interact, which enabled him to prove, actually, that if an object has six symmetries, then either its symmetries behave in the same way as the triangle or the six-pointed starfish. So it enabled him to abstract the idea of symmetry underlying something. And this is perfect now when we go to the Alhambra, because if we look at the tiles on the walls in the Alhambra, how can we say when two of those walls have the same underlying symmetry? Now, they might look geometrically very different, but Galois' language enables us to say, actually, the symmetries of these two walls are the same symmetries, although they look very different. So we've got this beautiful wall with these little twisted triangles, and here I've got the six-pointed star with these kind of Zs. So let's look at the symmetries of these two walls. Remember, symmetry are the magic trick moves. So I can pick up these tiles, rotate them by a sixth of a turn around the point where all of these little triangles meet, and then they all line up again. So that's one symmetry, a sixth of a turn around there. But I've got another symmetry. I can fix the point in the middle of one of these tiles and rotate by a third of a turn there. And they all line up perfectly. Now there's another rather hard symmetry to find, but if you actually fix halfway along an edge, you can actually fix that point, rotate all of them by 180 degrees, and then suddenly all of them fit perfectly down on top of each other. It's quite fun. I mean, this is the fun thing about going to the Alhambra, at least for me as a mathematician. It's trying to find, where are all of these points where you can fix things, rotate them, or reflect them. And if you go now to, so you've got those points there, but you see the same symmetries happening on this wall, which looks very different. Rotate by a sixth of a turn around the point in the middle of the six-pointed star, everything matches up. The third of a turn is actually where all of these Z pieces meet. So again, rotate by a third of a turn, and eventually, ping, third of a turn, everything matches up. The half one is really difficult to find. It's halfway between the two six-pointed stars. Here, if you rotate everything, you have to rotate it by 180 degrees before it all matches up. But so although these walls look very different, Galois' language says, but no, the symmetries will interact in exactly the same way. In fact, you could put one wall on top of the other, and whatever symmetry you did to one wall will give you a symmetry of the wall underneath. So this group of symmetries, we give the name 632 because of these three different sorts of rotation. Here are three different, well, this is actually the tiles that we met when we entered the Alhambra. This is actually the ceiling in that first room in the Alhambra, and this is the tiles on the floor. Now again, these pictures look very different. But the underlying symmetries, thanks to Galois' language, we can say are actually the same. And this group of symmetries we call 442, nothing to do with football, but because of the fact that there's a place where I can rotate by a quarter of a turn, a different place here, and here again somewhere where we have to rotate by half a turn. So Galois' language is absolutely extraordinary. I think it does for symmetry what the idea of number did for us many years ago. I mean, the concept of number is very abstract. For example, I've got 1, 2, 3, 4, 5, 6 people on the front here. They're sitting on 6 chairs. Now, the people are very different from the chairs. You'll be glad to hear. But the abstract idea of the number 6 is common to both of them. But we've abstracted this idea of number, which is common to things which have very different physical manifestations. Galois did the same thing for symmetry. These walls look very different, but he's found a way to abstractly say, no, the symmetries underlying them are actually the same. And using those kind of Sudoku rules, it wasn't Galois, but mathematicians at the end of the 19th century were able to then say, well, how many different symmetrical games are there? If these are all the same, well, how many different ones are there? But using this language of Galois, we discovered there are actually only 17 different symmetrical designs that you can make in the Alhambra. And actually, one of the games we played in that chapter, the month of October, was to go and see, did the Moorish artists discover examples of all 17? They were incredibly inventive with the way that they tried different shapes and things like that. Very often they repeated things like the 632 or 442. In fact, it took me several days, but we managed to find examples of all 17 there. But I think it's the power of mathematics to say that however hard you try, you're not going to be able to make a new symmetrical wall which is going to have symmetries different from these 17. So I can describe this symmetrical tile using numbers. It's a tile which has points at 0, 0. Then you move one step north to 0, 1, one step east to 1, 0, an extreme point at 1, 1. 3 dimensions, well then I can use the height above sea level. So I use 3 coordinates, 0, 0, 0. I can describe all of the points on a 3-dimensional cube. Now, if I want to make shapes, symmetrical shapes to tile my Alhambra in higher dimensions, I've run out of pictures. We don't have pictures of 4-dimensional shapes. But the wonderful thing about Descartes' dictionary, this power of the language of mathematics, is that actually I can describe for you a 4-dimensional cube. It starts at a point at 0, 0, 0, 0. And then it has edges running to 4 points at 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, all the way through to an extremal point at 1, 1, 1, 1. I think that is the power of mathematics. You know, although I didn't realize my dream to become a diplomat, come here to Brussels to represent my country or whatever, actually I ended up learning another language which allowed me access to a very strange country. In a way, I say I'm an ambassador for the world of mathematics. And so that's what I spend my research doing, is trying to explore this world of symmetry. What other... We know there are 17 in the Alhambra, but what about the Alhambra in 4 dimensions, 5 dimensions? So actually, that's what I spend my life doing, creating symmetrical objects. The exciting thing for me about mathematics is, although we understand the symmetries in the Alhambra, there are still many things about symmetry we don't understand. And I think that's what, for me, makes mathematics so exciting. It's a living subject because of all the things we don't understand. I actually always love coming back to this quote that my professor in Japan that I work with told me about, because I think it sums up why mathematics is a living subject. In everything, uniformity is undesirable, and leaving something incomplete makes it interesting and gives one the feeling there is room for growth. So in some ways, it's all the unsolved problems, the symmetries I don't understand, which make mathematics such an exciting living subject. So, thank you very much.